Okay, as I mentioned, sound in small rooms, very difficult because of the symmetry of the room and the resonant frequencies that get created in the room. There's a few tips that you can use. The placement of your speakers are critical. Experiment a little bit with where you put your speakers. Never put your speakers in a corner. Sound builds up in a corner. Try not to put your speakers next to a corner on one side and not on the other side. You want to put it in the center of the wall so that they're balanced. Even if sound builds up on the corners, it's going to build up equally and not make the speaker sound lopsided. Symmetry of where the equipment's placed. Absorption, a little absorbing panels helps a lot in terms of sound reflection. These guys only really absorb higher frequencies, but those are the most irritating in terms of listening. Low frequencies will still reflect through it because this is a very thin little pad and low frequencies are really big. So that's not a big deal for low frequencies, but for high frequencies that really get irritating. That's like a bathroom reflection, is a lot of high frequency. For low frequency, to capture low frequency is much more difficult to absorb and stop, and that's why they put bass traps in. And a bass trap is like this big sort of in fact, in my studio, used to be a little living space that I turned into a studio, and in the back of the room behind the speakers I've got a fireplace that was a working fireplace, and I took and I stuffed the chimney with foam, and now it's becoming my bass trap. So bass frequencies that are really long go in there and they get absorbed in the chimney and never come back. It worked really well. It was just an example of trying to use what actually existed in the construction to my benefit, knowing how sound behaves. And here's a great example of sort of a low-cost way of figuring out what's going on in your room a little bit is take a flashlight and use a mirror, because sound travels like the light would. At least this way you can see where it's reflecting. So you start at the speaker and point the flashlight at a wall, put a mirror on the wall, and you can see where the sound's actually going to reflect, right? Whether it's going to go to the listening area or behind the listening area, or in front of the listening area. The problem is that if you have like this kind of an example, my little picture there, so here we go. Sound goes this way, right? Two distances, right? And these want to be equal distances, an equal lateral. This is not drawn right. They're all supposed to be the same length. So sound goes this way and this way, let's say. I didn't draw it very well, but at some angle it'll actually reflect back to me. Here's a great example why it's important to remember sound takes time to travel. Okay, this distance and this distance are different. They're different. So what happens is, think of a sine wave. It takes a certain amount of time to reach you this direction takes a longer time. If it just happens to be 180 degrees out of phase by the time the longer path takes to reach you, that frequency is going to destruct itself, right? If it happens to be 360 degrees of a specific frequency, then it's going to be reinforced. Then it's going to be double loud. That's why your room interacting with your sound can really make a drastic difference. Or this path that eventually gets to you, right? Smaller rooms reflect more times because it takes less energy to keep bouncing around. So the smaller rooms have many more paths to reach you and really confuse you. Okay, let's talk about sound generation, because this is really where it gets fun. Because we all work with sound. You either play an instrument or you hear, you go to the symphony, hear stringed instruments. There's a lot to do with sound generation from stringed instruments. When guitar players play a harmonic on an instrument, I should have brought a guitar. You pluck the string, then you touch maybe at the octave fret, not very hard, but just enough to touch the string and not press it down to the fretboard. And then you get an octave frequency harmonic. That's because you're touching a nodal point. That's the spot where it's effectively changing the length of the string to half as long, and it'll resonate an octave up. Right, a string. Now there's formulas for all of this, and this is a resonant frequency. So let's just talk about how a guitar generates sound. It's an acoustic guitar. So it's got a string, it's got a body that's hollow with a hole, and it's generating sound, right? So you put energy from your hand, you pluck the string then vibrates. The vibrations of the tension of the string, the length of the string, the mass of the string creates certain standing waves that reinforce itself and reinforce the cavity of the guitar, the size of the guitar, has certain resonant frequencies. So that's why some guitars sound boomy, some don't sound boomy. They all have different sounds based upon their shape, their size, and so on. For example, if you're recording a Martin guitar, it sounds really full and rich in the room, but it tends to be boomy when you record it with a microphone. If you're recording a Gibson guitar, they tend to record very well, but in the room, they sound a little thin. So it has to do with the type of guitar and how it sounds. And that has to do with the size, shape, and resonant cavity of the guitar. So that's how a guitar generates sound. Same thing with a violin, same thing with a cello, same thing with a viola, all stringed instruments basically. All of it starts from the energy that you depart into the strings. And the energy that you depart into the strings starts this resonant frequency and resonates the wood or the cavity of whatever you're working with to create a sound. Here's another example of strings, and based upon the length, specific frequencies that can resonate. The same thing applies if you've got a tube and a column of air with two opens on each side. That means it's an antinote on each side. If you've got, say, a Coke bottle that's closed on one side and open on the other, and you blow air into it, it's going to create a tone that's like a note on one side and an antinote on the other side. Right? Because the fixed side is the closed end of a tube. I don't want to rush through this too much, but Helmholtz resonator is basically what you create when you blow over the top of a bottle. It's a fancy name for basically talking about a resonance of an enclosure. So you blow over the top of a Coke bottle, let's say. They don't have Coke bottles anymore. Well, any bottle, wine bottle. Right? It's a closed bunch of air inside of there. You blow into it, you excite energy into the air that's inside, it resonates at a certain frequency, pushes down, pushes up, you keep blowing, it pushes down, pushes up, and it resonates. And it resonates with a frequency, a tone, a pure tone pretty much. That's called a Helmholtz resonator. But that's how horns work with the same principle. How you can excite a resonant frequency in a column of air is the same way. So two open ends end up becoming two antinodes. Instruments with conical pipes, bassoons, oboes, saxophones, closed pipes, organ, and so on. So this basically, flute is closed on one end, open on the other. All of these kinds of shapes create different resonances and different harmonic structures. Same thing with a piano. I recently looked at our piano, and underneath there's a soundboard. The harder you hit the keys, the more the string resonates, the more it excites the soundboard, which vibrates. The thinner the soundboard, the more sensitive the keys are. So you hit it softer, you get a different harmonic structure than when you hit it harder. So all of this relates in a very general way, and that's all I really wanted to point out, is that basically stringed instruments, wind instruments, they all create resonant frequencies like when we discuss the resonance inside a room. Except this we're trying to harness for musicality to create a musical situation. Now on a flute, as you open keys, you create different nodal points because you've got an opening and a closing. So if it's all closed keys, it's the length of the flute. You open up halfway in, it creates a shorter length to resonate. It creates a different tone. So here's an open situation, right, where the open end is the node. So this is a quarter of a wavelength. So they all create different tones based upon the size of the instrument, like a sousaphone play lower notes than a trumpet, right? Because of the length of the tube and all of the way that the open end, closed end kind of resonances work. No, what I was saying is that a room has a resonant frequency, just like a tube does. Just like when I was a kid, I was really industrious. I was a very musical kid. I took a garden hose, 3 feet of a garden hose, wrapped it up, put a funnel on one end, and blew into the other end and made a little bugle, right? Because the length of the hose, if the hose was longer, I would have gotten a lower tone because of the length of the hose. That's 2 open ends. If you talk about a closed end, like what's exhibited here, that's more like blowing into a bottle, right? 1 closed end, 1 open end. A flute, 1 closed end, 1 open end. Trumpet is open on both sides. So different instruments have different qualities in terms of the wind instruments. The stringed instruments we discussed, like a guitar, all of the stringed instruments operate the same way in generating sound. So it stands to reason that the larger the instrument, for example, a bass or a cello, compared to a violin. Violin, much smaller, resonates at a higher frequency because it's smaller. Larger instruments resonate at lower frequencies because the wavelength is lower. It takes more energy to develop sound in a bass instrument. You have to hit it harder, pluck it harder, resonate more to generate volume of sound because all of that wood has to move to resonate to generate the tone. Violin's much lighter, much smaller, takes less energy. Ties together again. Higher frequencies, less energy, lower frequencies, more energy. It's like one big picture that really does tie together. And I'm trying to give you different examples of different ways of thinking of it to understand the same basic principles. But you can see from all these examples how it really does all coordinate. To get the basic language and understanding of the concept of how sound works is super important, and I do 1 week on how we hear, because those two things, how sound is generated and how we hear, are basic principles in how to be able to record it properly and play it back properly. Now that we've got the language, you can look at a situation and people come up to me and go, well, how would I mic that piano? And I look at the piano and I think about how is the sound generated in the piano? Okay, you hit the key, the string moves, it generates the soundboard, resonance. Okay, I'm going to put a mic here because that's a good place to capture the sound that's being generated. And now that you understand that, you can be able to place microphones in more strategic spots that actually sound better. So, the object of being an engineer isn't to just make sure you get all the mics everywhere. It's to know what you're doing and why. And now after this class, you'll understand how a guitar works and where maybe it would sound best based upon what kind of sound you're looking for.